Hi, welcome to Lesson 20F, Variance and Standard Deviation. The goal of today's lesson is to learn about the power and beauty of variance and standard deviation. We've seen range, we've calculated the range before, we've also calculated the interquartile range. The little problem with these measures of dispersion of data is that range just uses two values. The maximum value minus the minimum value. And the interquartile range also just uses two values, the third quartile and the upper quartile and lower quartile. Those are just two values. So it's really hard to get a real sense of the dispersion or the spread of the data from two values. So there's somebody came along with this great idea to calculate variance and standard deviation. So suppose we've got data values. There's n data values, and there are x1, x2, x3, x4, etc., 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 all the way up to xn. We know that the mean, we use the symbol x bar for the mean, and if we were to take x sub I and subtract that from the mean, that would show us how far each individual data value, x sub I, whether it's x1, x sub 2, x sub 3, etc., is from the mean. So it's the difference from the data value to the mean. If we were to add all these different x sub I, so if we did x sub 1 minus the mean, x sub 2 minus the mean, x sub 3 minus the mean, x sub 4 minus the mean, etc., 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 we would find that the sum of all that would equal 0. So if you do the sum of x sub I minus x bar, for all of those values from I equals 1 up to n, the sum of all those would end up equaling 0, because with the mean you've got the same number of values below the mean as you do above the mean, so it all ends up working out. So if we were to, there's a calculation called the variance, and if we were to calculate the variance, what we would do is we would take this part here and square it. And if we square that deviation part, how far it deviates from the mean, then it would not equal 0. So we get a final value. Okay. So what we're going to do is the variance itself is written as s sub n squared, and that equals the sum from I equals 1 to n of x sub I minus x bar, all squared, and we divide that by n. Okay, and that is the calculation of the variance. That tells us the variation or the deviation of each data value from the mean. And the square ensures that none of the terms are negative, therefore this will not add up to become 0. If this variance ends up giving you a small value, then it tells you that most of the data values are close to the mean. Okay, so that would indicate that there's not much deviation from the mean. The deviation from the mean is very small. So if this variance, hence the root of that being to vary, if the variance is small, then that means it's close to the mean. Okay, and by dividing this by n, that indicates on average how far the data is from the mean. Okay, so it's giving an average itself, an average of the deviation from the mean. Okay, so it's further averaging this. So that's all fine and dandy. Now the only problem is is depending on the units that we're using, we could get some sort of units, say kilograms squared, or we could get times squared, etc. And some of these units may not make sense, after we square this. So there's the further calculation called the standard deviation. Again, it's a deviation from the mean, and it's standardized because we're going to be taking the square root of the variance. And what that does is it just puts the units back into a normal form. So instead of having a square unit, it's then like a square kilometer or kilogram or a square time. It would just be kilograms or time. Okay, so the actual standard deviation formula is exactly the same as the variance formula, where we have xi minus x bar all squared, and the average of that, but then we take the square root of all of that, and then that will clear up all the units for you. It's the most commonly used measure of the spread of data, and for a sample is represented by S, or S sub n, I suppose, and for a population it's sigma, so the lowercase sigma. So this is for a sample, and this is for the population. But as we've said in the past, if you've taken a proper sampling, so 10% of the population, then the sample will do as a representative of the population. So we don't have to worry about the population itself. The sample will do for those results. And the larger the standard deviation, just the same as, the same sort of thing as the variance. If the standard deviation is large, then that means that the data is more spread out, therefore it's less consistent. If it's a smaller standard deviation, just like with the variance, it means it's closer to the mean, it's not as spread out as much, and it's a more consistent set of data, so we can, it's more reliable, that is. The standard deviation, because we're using the mean, it is a non-resistant measure of spread. Okay, so just like we talked about in the past, the mean is non-resistant measure of spread because very high values or very low values will really change, they really affect the mean, whereas median is a resistant measure of spread. So the standard deviation is a non-resistant measure of spread because of the dependence on the mean of the sample. Now it's basically only a useful measure of the distribution if the distribution is approximately symmetric. Okay, so if we have a symmetrical distribution, so suppose we have something like this, then the standard deviation is a useful measure of the distribution. This is, again, as I mentioned before, I believe, this is normal distribution, which we'll get to in chapter 24. But if the data is skewed in any way, then the interquartile range, or the percentiles, this isn't the correct short form for that, but I'm just writing it like that anyways, the interquartile range of the percentiles are a better they're a better measure of distribution if there's a skew, if it's skewed to the right or skewed to the left. And when we find the standard deviation for group data, or data that includes different frequencies, just like where we found the mean of group data, where we had for example, 5 from this set or 7 from this set, we did that fx calculation. So for standard deviation, we're going to do the same sort of thing, where we have S sub n is the sum of f sub I, which is the frequency, of x minus xi minus x bar all squared. So there's the distance from the mean squared multiplied by the frequency of entries in that group, and then of course divided by n, and then take the square root to correct the units. So that would be used for group data or continuous data where it's grouped into classes, etc. Okay, so and remember that when we are using grouped classes or group data in classes, we're going to be using the midpoint of the interval to represent the data in that interval. Okay, so that pretty much wraps up the idea of standard deviation for individual data values and group data. And so in class tomorrow, what we're going to be doing is we're going to be looking at an investigation from the textbook. I'd also like you to look at the examples. We're going to look at example 12 on page 533. We're going to be looking at example 13 on page 536. And we're going to be looking at example 14 on page 537. So that's what I'd like you to do tonight. And if you can take a look at the practice questions here, you don't have to do all of them. Maybe just take a look at them for a few minutes tonight, and after you go through the investigation and the examples in class tomorrow, you can work on the rest of the practice to enhance your skills in class. So again, thanks for watching, and we'll see you in class.